So today we'll be covering higher order approximations. In the previous lecture, we covered using linear approximation. So what we've done so far, we went through how to develop the partial differential equation or ordinary differential equation for a physics problem. Then we walked through to how to approximate the solution over a domain for that differential equation. And we used three methods: strong formulation, weak formulation, and then in some cases there's a functional that can go along with that differential equation, and they're connected through the weak form, and you guys have seen that through your homework. And then in those cases you can use the functional and then solve the problem using the Riley-Ritz method, right? Those are the three methods we learned. And then after that, I've shown you some examples where approximating the solution over the full domain, it may not be practical. Did everybody finish that one problem? Was the second problem of the last homework, where there was a beam on an elastic foundation. And the solution should look like there's almost nothing happening at the center, basically, of that beam. But as you approach the edge, there's something called the boundary layer effect of structural mechanics, where things very, very quickly, okay? This problem actually exists. This actually occurs when you have a pressure vessel that has end caps. So if you have a pressure vessel with an end cap, the pressure vessel expands almost very uniformly in the center of the vessel. And as you approach the end caps, you get the same effect. You get this exponential, almost exponential effect, where the displacements change considerably, almost immediately, okay? And that's why I gave you the problem, because I want you to see, I think you may have seen that you used an approximation function. And that approximation function did not do very well, did it? No. It did not do very well, right? So, but you could have increased the number of elements in that problem, sorry, the number of coefficients in that problem. And what you have seen is that it's getting there, but not quite, because it's kind of hard to actually fit any, go to Excel and try to fit a polynomial on that particular solution, and it will be very difficult to do, to try to get a good match. So in that problem, I think that's a good problem where you will use finite elements, because you will divide the domain in smaller pieces, right? And then you can take the piece where things are changing very quickly and put more elements there to try to get the behavior a little more accurately, okay? And so I'm motivating for you very quickly why we need finite elements, and also we're getting a better understanding on how to get there. And what we've done in the previous lecture, we approximated the behavior over an element. You know, and instead of the whole domain, we approximated the behavior over the element, and then we found that these unknown coefficients, which had no meaning, with weak formulation and Riley-Ritz, we can reformulate the problem in a way where the unknown coefficients now are the unknown quantities at the nodes. And so now I have basis functions that go along with these unknown quantities, which are nodal values. And these basis functions now have meaning also. They have some properties, such as partition unity. They have a property such as Kronecker delta. And today what we're going to do is we looked at a possible solution in the previous homework, previous example. We saw a problem where the approximation using linear approximation was not as good. And the exact solution, you know, is over here, and I'm over here, right? So the linear approximation over each element was not as good. And so today we're going to look at ways to refine that, how we can get a better solution. There's two ways to accomplish that. The two ways are, one way is to increase the number of elements. I could have increased the number of elements and then get closer to the solution. Another possibility is to increase the order of approximation over the element. So in the previous lecture, we used a linear approximation over the element. And then now, today, we're going to be using a higher order approximation over the element. That's one approach. So in one case, you can increase the number of elements. In the other case, you can increase the order of approximation over the element. Okay. And so if I'm going to use let's say I want to use a quadratic approximation over an element, right? How many unknowns do you think I will have? How many unknown coefficients I have in a quadratic approximation? In a linear approximation, we had 2 unknown coefficients. In a quadratic approximation, how many unknowns do you think we will have? 3 unknowns. That makes sense, right? But I want to relate that to nodal quantities, right? So in the linear approximation example, we had unknown quantities were the values at the ends of the element, right? At the 2 ends, right? But if I go quadratic and I want to relate it to nodal quantities, I still have 2 unknowns at each end, but I need 3 unknowns. Where can I put that 3rd unknown? I'll just put it in the center of the element, maybe somewhere in between. What about that? Is that okay if I do that? Yeah. Let's do that. Okay? So the one approach, in one case, linearly interpolated between these 2 points, right? And in this case, we can now look at a quadratic interpolation between these 2 points. Here I have a 4-element bar model. I need 3 data points to fit a quadratic polynomial, right? That makes sense. And so to do that, let's consider element number 3. I have a node here and a node here. So at least I have 2 unknowns. What I can do is add a 3rd unknown right at the center. I could move it more to the left or more to the right if I want to. I can do whatever I want with that node. Okay? So if I were to do that, I can start with my approximation function. The approximation function is u tilde alpha 1 alpha 2x plus alpha 3x squared, just like you did in weak form Galerkin, strong form Galerkin, and right arrays. Just like before, we need to satisfy the continuity requirements. In the bar element problem, we have determined that the displacement must be continuous across element boundaries, and we found that by looking at the essential boundary conditions of the problem. The good news is that if I have a middle node here, that node is in the middle of it. It does not connect to other elements. You see what I'm saying? This node K is not connected to any other element. So I don't have to enforce any continuity here, just across J and across I. That's all I care about. So if I were to now look at trying to find, because these unknown coefficients have no physical meaning, and I need to connect it to other adjacent elements, what I will do, I'll take my polynomial that I assumed, the quadratic polynomial, and I'll evaluate xi to get the value for the displacement there. So I'll make it ui. I evaluate at the other end xj, and then find the value there, which is uj. And so now these ui and uj, which are here and here, are connected to adjacent elements. Okay? And they have physical meaning. You know what they mean. You get the value and you know what exactly it is. It's the displacement. Not only that, you have an approach for assembling the system together. And then I have a middle node somewhere, xk, somewhere between I and j, and then here has a value of uk. Okay? And it doesn't have to be right in the center of the element. I can have it offset if I need to. Okay? Using these 3, and don't, you're going to see a lot of math on this, but I think you'll follow it if you keep a simple mind approach. I always tell my students mathematics can look very complicated, but I think it's because we make it complicated. Honestly, it's not that hard. Just look at the problem slowly and carefully. Don't be scared of all these symbols, okay? There's no need to get scared of that. So if I go here and I look at, that was my polynomial, right? And the angle, what is my angle? My angle is to have an approximation function over the element that's written in terms of unknown coefficients that are made up of those nodal quantities, ui, uj, uk. That's really my angle, right? So having it in this format is not the best. So what I need to do is plug in xi here, and I know that's ui, and xj, I plug it in here, and I get uj. And remember, these xi, xj, and xk, they're known quantities. Just assume this could be 0, this could be 1 squared, and this could be 2 squared, that's 4. You know, these will be numbers, and I think there's an error there. This should not be 2. So if you can take a note, so that would have been 2, this will be 4, right? So these are numbers, okay? But I'm making general because I think it's important to understand how things look in a general manner, okay? It depends where the element is positioned, right? That's how this xi, xj, and sk is. How does that relate to Abaqus? In Abaqus, if you've seen already, or Nastran, or whatever software you want to use, you have to define a node position, remember? That's a star node, and you define the nodal positions. And then the second step is to define the element connectivity, star element, and then you have the element connectivity at the bottom, right? So the element tells you what nodes go with the element, and those nodes have coordinates, right? That's how I know what's xi, xj, and xk. That's how I know this, okay? And so by equating this to that, what I need to do now is I need to find alpha 1, alpha 2, and alpha 3 in terms of ui, uj, and uk. That's my goal. And if I can do that, I'm getting in a closer where I need to go. So if I put this in matrix format, this is how it looks. And this is a matrix of numbers, by the way. These are all known quantities. If I know the element location, I know xi, I know xj, xk. I know all this. And so I want to write alpha 1, alpha 2, and alpha 3 in terms of ui, uj, uk. That's my goal. I invert this to get basically alpha 1, alpha 2, and alpha 3. And then once I get alpha 1, alpha 2, and alpha 3, what I'll do, I'll plug this in here, back in here, okay? So that now I have u tilde x. U tilde x now becomes an expression of what? Sorry? UI, uj, uk, right? Because I substituted alpha 1, alpha 2, alpha 3, so it goes all the way down to UI, uj, uk. That was my goal, okay? Now, we can do that very succinctly. I take the inverse, I plug in alpha 1, alpha 2, alpha 3 here, okay? And then here, I will have what I really want, after I plug it in here, I want to know what the UI, whatever goes against that, plus UJ, whatever goes with that, plus UK, whatever goes with that. Is that correct? Yeah? Yeah? Isn't that what I want? Yeah. So if I have this approximation function, now everything is in terms of UI, UJ, UK. How do I find those coefficients? There's a clever way. There's a very clever way. If I take the derivative of u respect to UI, I will find exactly what goes with it. Because everything else will go to 0. It's a really quick way of doing it. And if you don't trust me, do it at home, and it's going to work out. So I took the derivative of u tilde against ui, and I'll get actually the shape function. And you can see it here, actually. Take the derivative of u tilde against ui. What do you get? N. I don't have to care about any of that. Take the derivative of u respect to uj. What do you get? There's no uj here. It goes away. uj is there. I get nj. Right? So I have a very quick way of doing this, getting these coefficients. And the basis functions. These are the basis functions which we've described as the shape functions. So this is exciting because now, you know, when I was preparing for this lecture, all I have to do within a couple of minutes, I went to Mathematica very quickly. I calculated the inverse. And I don't know if you understand Mathematica language, but at least I have the code here in case you want to, do it at home. And if you want the code, I can give it to you. It took me a couple of minutes. I took the derivative of that, I took the inverse of that, to get alpha 1, alpha 2, and alpha 3. Then I plug in that into my approximation function. And then I took the derivative of this with respect to ui, and I got the shape function for each of them really quickly. And just to check that it works, I added all 3 shape functions. What should I get for when I add all 3 shape functions? 1. This is a partition unity. And I did the check here. M1 plus M2 plus M3. I just call these things M1, M2, and M3. And it gave me 1 really quickly. Okay. Now, these expressions look very complex, actually. But they're not complex. And I'll show you how not to get too concerned about this. So here are the unknown coefficients. Here is my basis functions. Here's my basis functions. And the basis functions, all I did, I went to Mathematica and wrote it out very nicely here so you can see it. And I want to make some observations very quickly, very quickly. When I plug in xi for shape function I, what happens here? Xi minus xj, xi minus xj. What happens there? 1. Xi minus xk, xi minus xk. 1. Excellent. So this is great because now let me plug in xi at the other nodes. What happens when I look at nj evaluated at xi, at node I? 0, because I have xi there, that goes away. Evaluated here, this is 0 also. So you can see quickly that ni is 1 at its own node. But the other shape functions at node I are 0. That's a Kronecker delta property we talked about, right? Is everybody following? Excellent. Excellent. Okay. And now we can look at what's happening at node J, which was on the other end. Remember we had 2 nodes at the extreme, I, J, and K was at the middle. Let's try with J. So at xj, xj minus xi, xj minus xi, 1. xj minus xk, xj minus xk, 1. Great. And nj is 0 at the other 2 nodes, I and k. You can check it. Because if I plug in xi, goes away. If I plug in xk, goes away. And if I add all these 3, I get 1. Okay? So these shape functions are great. They meet the properties we talked about. They are my basis functions. I can use them as basis functions. They're complete. You can check at home. They're linearly independent. Linearly independent, complete. And not only that, they allow us to have these unknown coefficients, which are connected. Maybe ui and uj are connected to adjacent elements. Okay. Again, Kronecker delta properties in the partition unity are satisfied. So let's look at what's going on here a little bit more carefully. But let's take an example now with xi is 0, xj is L, and then I'll take a middle node, xk equals L half. Okay, we're going to do that. And so if I take this example and I plot the first one, you can see that it starts at 1, and it goes to 0 at the middle, and then goes to 0 here. That makes sense. And if I take the middle one, it's like a parabola. It is a parabola. And it's maximum here at the center, 1, and then 0, 0 here. And then finally, I have, again, this third one, which goes with this guy here. You can see very quickly how it goes to 1, but 0 and 0 there. So with numbers, you can also see that it works out. The second thing I want you to follow me in this journey is to look. I want you to practice with me. I think it's obvious, but I think you need to practice this with me so that when I go to the next problem or the next example, you can follow me. Okay. So if I look here carefully, can you quickly see that when I plug in x equals L half, it goes to 0. You see that? Yeah. And when I plug in x equals L, it goes away also, right? But I want to look at something also very interesting. Is when I plug in x equals 0 here and 0 here, what do I get here? L squared over 2. L squared over 2. So what coefficient do I need to make it 1? 2 over L squared, right? And so now here, let's look at this example. So when I have this middle node, is 0 here, obviously. Is 0 here. L minus L is 0. Great. It's working out. But when I plug in x equals L half, I get L squared over 4. So I need to multiply by 4 over L squared to get 1, right? Yeah? And the same here. I can repeat that. And the reason I'm kind of walking you through that process is because you can actually derive the shape functions without following this process. Without doing any of this, you can actually come up with the shape functions, okay? By just with that information. And I'll show you with an example so you can see how to walk through that, okay? Let's take this example. In this example, xi is 1, okay? And don't look at the solution. I probably have it here at the bottom, but I want you to think through it with me. Xi is 1, xk is 6, xj is 7. Let's look at shape function 1. Somebody tell me, what is the value of shape function I here and here? 0. So if I plug in these values in my shape function, I must have an x minus 6 and an x minus 7, right? I have to have that so that those go away, right? So the very minimum you see here for shape function I already know is x minus 6, x minus 7. Everybody agrees. And if I plug in the value of x at 1, what do I get there? Minus 5? Yes? You're not participating. 1 minus 7? Minus 6. What is the multiplication? 30. That's not giving me 1. So what coefficient I need to make it so I get 1? 1 over 30. I just derived the shape function without doing all those steps that I did earlier. In fact, I have it right here. Okay. Let's do another one, just because it's kind of fun. Let's look at node j. Node j, shape function that goes with this has to be 0 here and here. So then I must have x minus 1 and an x minus 6 for that to go away there. Okay, so again, am I lost? No. X minus 1, x minus 6 times c. So this must be 1 at this location, So 7 minus 1, 6. 7 minus 6, 1. So I have a 6. So c must be 1 over 6 for this to work out. Okay, so that's shape function nj. And then I won't do the next one because I think at this point you get it. Okay, but the shape function, my approximation function, just looks like this. With numbers, looks very nice actually. And you can see very quickly that it doesn't look that bad. It's just, that's the shape function. That's my approximation function. That's my approximation function. These guys right here are the basis function, okay, that correspond to each of these nodes, ui, uj, uk. And in fact, if you add all this together, you should get 1. Okay? You should get 1. All right, any questions on this? Any questions on this? I have a question in the back.
What's the shape function? What is the value of it?
The value of the shape function.
In terms of what's physically being modeled.
So the shape function, what the shape function is doing, first of all, is the basis function, which is very important because you're making the error, the residual function, orthogonal to the space of basis functions. The second thing the basis functions, which are the shape functions, are doing for you, they're allowing you to have the opportunity to have the unknown coefficients to be ones that have physical meaning. Okay? In addition to that, the shape functions, the basis functions actually have shapes. And they allow you to have two important properties, completeness and convergence, and we cover that. And to be able to have completeness, we should be able to represent rigid body motion. We showed that in the last lecture. And then we must be able to represent constant strain rates or constant temperature rates if you're looking at heat transfer problem. Okay? So the physical meaning of them is that they're more mathematically formulated to allow you to accomplish things you could not do before in that manner. Okay? And if we look at earlier lecture, we also saw these shape functions represent the global approximation functions. They're part of that set of hat functions that allow you to approximate a solution over the whole domain. Okay. All right. So moving on here. Yeah. So we covered this one. Okay. This is me. I was going to show you how to do it again, but I think you got it with example, right? You guys get it with example. Now, if I go to even higher order approximation, higher order, say I want to go to cubic, do you need to follow the procedures I showed you here? These steps here? Excuse me?
Nope, not necessarily.
Why? Why don't I have to follow these steps? Sorry?
You could still use the other method.
I can just, yeah, I can use the other method here, which is very quick. So if I don't go to cubic polynomial, how many unknown coefficients I will have? 4, but I have 2 endpoints to the element, so then I'll have 2 interior nodes. And then what will I do to define the shape function? Well, shape function I, say, must be 0 at these 3 other nodes. Then I must have x minus j, x minus k, x minus l, make it up, the variable, right? Then I plug in the value for xi, and I figure out what the coefficient should be so I can get a unit value. You follow me? That's all I wanted to explain here, but it's too mathematical. So I think we can skip this. Everybody follows this, right? Excellent. Excellent. So if I go now, the steps are very straightforward. I have the element, but now I have a middle node, or that node could be somewhere in between. I just put it in the middle for now, but it's xk, it's general enough. And I have my governing equation. I derive the weak form. Everybody here knows how to derive the weak form for this particular problem. And then all I have to do, okay, all I have to do is realize that I want to plug in for V, I want to plug in each of these n's because I want to make sure that for V, I select the basis function, which are the shape functions. So how many shape functions do I have here? 3. So if I need to have V select each shape function at a time, how many of these equations I will have? 3. How many nodal values I have? 3. So I'll have a 3 by 3 matrix that represents the element behavior for this particular problem. Okay. And then for U, I'm going to plug in the approximation U. Okay. In matrix format, which is what I'll encourage you to work on from now on, because when we go to 2-dimensional and 3-dimensional, keeping track of everything can be very painful to write everything out. But if you can keep all this information in your head to some level, then you can operate with that and move fairly quickly. So you can see here that for U tilde I have to plug in ND, and then for V I have to plug in each of these basis functions. Okay, and then the shape functions are given here as a repetition. One thing that you want to notice too before you do anything without plugging anything in, you'll quickly realize I have a U prime and a V prime, right? Yes? We have that. So because of that, I want to calculate that derivative before I plug in anything in, just to keep things very simple. And so I notice that for U prime, I just can take derivative right here, right? So derivative of U respect to X is basically derivative of N respect to X, derivative of N respect to X, derivative of N respect to X. Everybody agrees with that? Yes. So we'll call this a new matrix, B. Okay? It's all about matrices. If I can give it names, I have less to write, right? That's the goal. Okay? And those are 261A. You're probably wondering why I taught you initial notation. But that's okay. I was also wondering a little bit about that. Matrix notation is a little bit quicker. A little bit quicker. Okay? Now, just to be fair, in 261A, we're dealing with, 27 unknown constants, Ci, J, K, L. We have to carry all of that. You cannot write a fourth dimensional matrix here. So just to be fair, we had to do it there. But we don't have to do it here. Okay, so we have B times D. Just memorize that. That's du dx. And, one more thing. One more thing. For V prime, you agree that I need to calculate derivative of Ni respect to X for that? Yeah? You agree that for the next one, I have to do derivative of nj with respect to x? You agree for the next equation, I need derivative of nk with respect to x? Aren't those the components I have here? Basically, just transpose it. Just transpose that. And then you have all, you're done. So let's see how I did that. I plug it in for each v, take one basis function at a time. Okay? And then u tilde is b times d. We already covered that. And that's all I got. Okay? The middle node doesn't have any external load applied, but I could have done that. I didn't do that, but that's what I have. In essence, I have three equations, three unknowns. And notice how this column here became B transpose. That's what you see there. Okay. And then this column here became N transpose. And then for P, I have PI, 0, and PJ. Okay. So notice that all I did, in essence, if you want to summarize, if you want to just skip all these steps, all you have to do is for U tilde, replace it for B times D. That's what we did there, B times D. Okay. For V, replace it for N transpose. And if you do that and plug it in, you'll get this right away. This formula right away. Okay. If I use Riley-Ritz, we covered this last time. But as a reminder, I can just plug in write it in this manner. For U tilde, I have BD. For U tilde, I have BD. And same process. Okay, same process. And then we cover that in the last lecture. And then we use linear algebra all the way down to arriving to this. Same thing we arrive with weak formularity. I don't want to repeat those steps. We cover that. Okay. Any questions so far? Any thoughts? Any conceptual gaps that we may have here?
Just a quick math question. What does it mean for the D, or for the second D to be on the outside of the integral?
So the question on the table is, what does the D transfer do outside of the integral?
Or not the D transpose, but the D on the right side of the dx. Is that?
This D represents the unknown coefficients, ui, uj, uk. And then this D here is ui, uj, uk, but transposed. So, okay.
So you can pull it out of the.
Because it doesn't depend. So the question is why I pulled it out from here. And the answer is because these are unknown coefficients. They don't have an x. They don't depend on x. Okay? Excellent. Let's look at an example. I think examples help a little bit. I'll give a lot of examples. Hopefully, that'll be enough for your homework. And also for your, I think your exam is you don't need any of this, actually. But you'll have fun. Okay? So let's look at this single element example, just one element alone. I just took one element. I have a distributed load Q. Okay, just by looking at this, what is the total force acting this way? Q naught times L plus PL. Okay, but I know that distributed force at least is Q naught times L, the effective force. You agree? These are the shape functions. If I select this to be 0 right here, and this to be L half, and this is L, you can derive this very quickly, and you will see that this actually works out very nicely. I just went in to Mathematica. Just let Mathematica do the work. I calculated B, so these matrices. I calculated that, that derivative, and the derivatives are given here. So each of these derivatives, just put these values here. Then you calculate B transpose times B, and then Mathematica does the wonder. It does the work for you, even does the integral for you. The integral from 0 to L, EA, B transpose B, and then gives you all these numbers. Okay? If you want to use MATLAB, you can use that as well. I haven't tried it there. Okay, so that's what you get for the stiffness matrix. Just a single element, so I don't have to worry about doing assembly in this example. Let's look at the forces. I have a distributed load, Q naught. So then I have Q naught Ni and Q naught Nj, Q naught Nk. I take the integrals, let Mathematica do the work, and I get Q naught L 6 Q naught L6, and then 2/3 QL. Okay? And so if I were to plot this here, I get this one goes there, and this one goes there. Anybody guess what is the addition of these three? Add it up really quickly. Q naught times L. Isn't that what I should get for the total distributed force? It's working. But the cool thing is that finite elements told you how much to put in each node. Because you doing it on your own will be really hard. It's a quadratic approximation. It's unclear how much to put in every node, but the math works out. And you can see very quickly how automatic the process is becoming. That's what I'm trying to prove to you as we move through this class. Okay. All right. Good enough with that example. And finally, I have the values here. I have the first node is fixed on the left-hand side. And then I have a reaction force because of that. And on the right-hand side, I have a load applied. So that's my distributed load contribution. This is my point load contribution. You can just solve this very quickly for U2 and U3. Okay? And once you have U2 and U3, plug it back in here, and then you can get the reaction force R1. Okay? And if you've forgotten how to do this, cross the first row, the first column, focus on this equation right here, solve for U2 and U3, and then you can go on from there. Any questions on that?
So this example was 2 elements or 1 element?
I did this is a one element example, quadratic element. So this is a single element from here to here, one element, single element. How many nodes? 3, because it's quadratic. Okay? Are you following? One element has 3 nodes in this example. Yes? Okay, good. Okay. Example 2. Example 2. This example has a purpose. It made my life hard because I had to create the example. But it has a big purpose. And you'll see that purpose on Tuesday, not today. I decided not to put you through the pain of the next topic. We'll cover it today. So I'm going to divide this domain. Okay, so first of all, this problem is a bar and has a distributed load that starts right kind of here. Okay, and ends here. And it has an axial load there. And then I'm going to divide the elements right there. Okay, so element 1 and 2. And then just for the kick of it, I made this. So this is one element, quadratic element, so it has 3 nodes. So this distance here, I made it L third, so I didn't put it right in the center. And I made this 2 L over 3. And then for this element, has again 3 nodes, 2, 3, and 4. I made this 2L and this 1L. Okay, these are all done on purpose. I could put it right in the center, makes more sense. But for the purposes of illustrating something later on, I need to do that. The code number is easy. If I don't want to deal with this boundary condition, I can just put 0 for the code number. I have 1, 2, and then 3 and 4. Okay. So for element 1, everybody agrees that I have 0, 1, and 2. For element 2, I have 2, 3, and 4. Excellent. So you can very quickly see that assembly is going to only be assembling stuff that has 2. Makes sense. The 1 and 3 will be disconnected from each other. Okay? They're not going to be connected in any way. Okay, I'll continue. So I did these things in Mathematica so you guys can see how I will have done it. And so what I did, and if you want the code, I can give it to you. I took the shape function and I created these functions here, xi, xj, hk. I did it because I knew I was going to keep using this, so I just did it this way. And this is how you define a function in Mathematica. So I define a function for I, j, and k. And then my approximation function is this guy here. For element 1, there's no distributed load. This is L third, and that's 2 L thirds. So what I did, I went to Mathematica. For xi, I start at 0, my coordinate system. So I put 0 for xi. For xj, I put L. And then for xk, I put L third. That makes sense because that's L right here, and that's 0. And that's about L third. So that's what I plug it in there. And then I did it the same for each of these guys. Since the function is already defined, Mathematica automatically gives me the shape functions ni, nk, and nj. Okay? Everybody follows that? Yes? Very good. I wrote it in a nicer format so you can see what I got, but you can actually verify it and you'll see it works out. The partition unity works out. If you apply Kronecker delta, it works out also. So you guys can check that. Then I went in and calculated these derivatives. And that derivative gave me these numbers. I did that here. I took those derivatives here. So derivative, this is how you get a derivative in Mathematica. You put a d in front and then comma x. Since ni, I have that expression already, it will give me that derivative automatically in this format. Okay? So I did it for each of the shape functions. All I did there was to calculate what you see above. Okay? Follow?
Yeah.
Very good. And then I let Mathematica do the magic. Integrate, right? EA, that's EA, remember EA, B transpose times B? So transpose B times B, integrate from 0 to L because the element goes from 0 to L. Let Mathematica do the magic, gives me a stiffness matrix 3 by 3, just like I expected. And I wrote it here again for your viewing experience. And then here is 0, 1, 2, 0, 1, 2. Everybody follows? You know how many steps, you know how long it took me to this problem? 5 minutes. That's correct. Okay? That's how quick this was. Okay? These homeworks should not take you more than 5 minutes, in my opinion. Okay? No, I don't mean that. It should take more time. But all I'm trying to say is, if you know the steps, right? If you know the steps, and if you're studying every day, you'll get it. There's nothing to it. Okay? And you don't have to memorize all these numbers. That's not what I'm asking you to do. I'm asking you to understand the process. Let the code do it. That's the whole point of FEM elements. The whole point of FEM elements, and you can ask, we have engineers in the back that actually work for companies. They put the hard work ahead, click the button, submit the job, the computer does the work, right? Is that, yes?
Yep.
It's not that simple, but yes. They're agreeing with me because they probably want a great grade, right? Okay, so we'll continue here. For element 1, again, I have no distributed force, so zeros across, right? Element 2, here, just keep in mind, it starts here at xi equals L, right? Where I left off with the other element. And I go to 4L, because my element length is 4L. Again, I plug in the coordinates for xi, xj, and xk, and I plug them in there. You have to plug in this correctly. If you plug this incorrectly, everything is wrong. So you have to have the coordinates of the element, the nodes in the element correct. You do that, it gives you the shape functions. Okay? I took the derivative the same way I did before, but you know, all I had to do was copy and paste from the previous element. All I did was change these numbers. And I could have done it much more automated. I was just trying to do it, you know, just to finish the work. But you can do this way more automated. And then let Mathematica do the magic. Now the integration goes for element 2. For element 2 goes from L to 4L. I have to be careful there, right? So notice how my two integrals, the first one went from 0 to L. This one goes from L to 4L, right? Now, you know, it will be more advantageous to have everything having the same integral limits, right? It will be very advantageous. That's why I have to keep changing this. And also, you know, Mathematica is not doing finite elements for us. It's Abaqus or code doing it. So I don't say integrate for me, right? I have to figure out a better way. And we'll talk about that as we move on. Then I took all this, put it here in this format, very nicely, 2, 3, 4, 2, 3, 4. And now I am ready to look at the force vector for element 2. I get here 3, 9, and 0. Okay. I was surprised for getting a 0 here. So I haven't figured out why I got the 0 here. So 10 points for you guys if you can figure out why I will have a 0 here. I don't know the physical explanation. I was trying to figure it out. But if you have a good one, please teach me. Okay? Okay? 10 points if you can figure out why for element 2 this node gets a 0 for force contribution from the distributed load.
Is the code for sure correct?
I think it is correct, but if you find an error, even more points then. Because then I can correct this PowerPoint. I think it's correct. But don't do this on expense of your exam or homework. This is just if you want to spend time. The bottom line is that you get the process. That's all I care about. And so for element 1, 0, 1, 2, 0, 1, 2. For element 2, 2, 3, 4, 2, 3, 4. And guess what? The only thing that gets assembled is the stuff that has 2 together, right? I have 1, 2, 3, 4, 1, 2, 3, 4. 4 nodes, right? I have 4 nodes. I had 5 nodes, but one of the nodes was fixed. So then I have a 4 by 4 matrix. Nodal forces, same way. For distributed forces, I have 0, 1, 2, 2, 3, 4. So these two get assembled. These get added together into this one. And the rest looks like this. And then for the concentrated forces, I have nothing applied except for the last one, PL. So I have a matrix, 4 by 4 matrix, stiffness matrix, global stiffness matrix, times a displacement vector, right, with 4 unknowns. And those unknowns, when I solve them, I know exactly what the displacement is right away. No conversion necessary. I know what the displacement is at every node. If I know the displacements, I know the strains. If I know the strains, I know the stresses. And you guys know how to go about that. In this example, if you were to run the example that I did last week with linear approximation, you'll get the exact solution. Because the exact solution is a quadratic polynomial. And so since I'm using quadratic functions, if I use this approach with quadratic approximation, I will be doing much better. Okay? So we're going to take a couple of minutes for a break here. So let's cover heat conduction now as example 3. Example 3 that goes for many different examples. It has 3A, 3B, 3C, and so forth. So far I've shown you examples with bars, but if you want to see how this applies to heat transfer, you have displacements. Typically is the quantity of interest in structures. In heat transfer, you have temperature. The quantity of interest in structures is stress or strain, and then here in heat transfer is heat flux. The boundary conditions in structures is a displacement fixed, or you apply a displacement. In this case, it's a fixed temperature. I apply a temperature to a node. In a structural problem, a force that you apply, a traction force that you apply, is in essence a heat flux that I apply in heat transfer. In a body force in structural problems could be gravity. But in heat transfer is internal heat generation. The unknown quantity, the empirical quantity in structures is Young modulus. Tells you how stress relates to strain. Well, in a heat transfer problem, thermal conductivity tells you the rate of heat transfer in the material through conduction of the material. If I look at a typical problem, you will have maybe heat flux coming in, and then you have a delta heat flux on the other side in a differential element. You can have heat generation. You can have convection, actually, from the sides, right? And so for heat convection, typically what you have is, say I have a body that's hot. Say that the calculator you have is heating up really badly. No, let's take the iPhone or the Samsung 7. It's burning, right? Sorry if you have one. I have one, so don't feel bad. Samsung 7, right? It's burning, right? It's hot. The internal heat generation is from the burning, whatever is going on, the chemical reactions, right? And I cool it in water. That's a convection problem because now the water is a cooler temperature and you have a heat transfer that's occurring from here to the surroundings. Is that correct? So that's called heat transfer convection, due to convection. And typically, there's a coefficient that tells you how good that transfer is. And that's called a heat transfer coefficient, which is given by this H. Okay? So every fluid has an H they can come up with. And for this example, H tells you how quickly you can get the material to the cooler state. Track? So in general, a heat transfer problem requires an understanding of how much energy is going in and how much energy is going out. But we know from conservation of energy that the energy has to remain constant. Okay? You cannot generate more energy than you have. And so here in this, if I put this into try to study this problem for a one-dimensional bar, I'll take a small dx, and I can calculate this perimeter around this circumference, and around this perimeter I have a dx, and so I can now write the heat transfer, okay, due to this piece, this dx being exposed to the surroundings. And so that'll be T minus Tf. Sometimes you use T infinity. Sometimes I use that. T infinity here means far field, but I use F for film, field temperature. Abaqus uses the words film temperature and uses the words film coefficient for this H. Okay, so you're going to see that if you go to the manual. And so now I can calculate, I can plug that into my equation for heat transfer. I have conductivity, I have convection, and then I can add another term for internal heat generation, which is in the next slide here, minus AQ equals 0. I have a minus sign here, so then you get a minus and a plus. Okay. Here I give you the definition for each variable. And the boundary conditions are typically temperatures are specified at the boundaries, or you apply a heat flux at the boundary. That's one approach. Another thing that I'm going to show you is that you can have a situation where you have a mixed boundary condition. I'll show you what that means in a couple of minutes. A couple of minutes means maybe 15 minutes. I'm not sure. Let's see how to formulate the problem. Let's see how we approach it. Okay, we've already seen how to do a bar, but I think I need to give another example so you can see, this works. So that when you work on your exam problem, because it's really a homework problem, the second part is a homework problem. The second part is a differential equation, right, also. And I'm going to show you the steps. First step, you have the appropriate physics, the differential equation that describes the physics. And the second step is to form the weighted residual. So I take, and I made it nicer so I don't have to write this ddx, I made it prime. So quickly made it prime. So this equation right here is exactly what you see there, but in a simpler format. All I did was to form the weighted residual. I took the residual function, which is this, made it orthogonal to the weight function. Okay, same steps as we've discussed to the steps to form the weight formularity. So very similar steps. Now I'm integrating from xi to xj because I want to look at an arbitrary domain, and maybe xi and xj here represent the nodes, actually, I to j, right? And so I'll go now, and what I will do now? I need to weaken the continuity requirements here. I have two derivatives. I would like to share half of that with the weight function here. When I do that, I integrate by parts. I put the v here, this one right here, and I carry the minus sign so I don't forget it. Carry it again, remove 1 prime, put it over here, plus, minus. This goes inside the integral, So minus times minus plus. Everything else gets transferred very quickly. And then I have this boundary condition here, v times kat prime. Okay. For the purposes of keeping minus signs here, so when I bring this to the other side, it's positive. What I've done, I made qi to be the minus of kat prime, and qj is kat prime. We know that q is equal to this. You know this from Fourier's law. So you guys know this. Just like in structural mechanics, force, right, was related to EAU prime, if you recall. Just like that, here we have Q is related to KAT prime. In this case, QI and QJ, the QI has been reversed in sign, but I'll show you later, don't worry, how that works. Okay? But the important thing is that this is minus and minus. I want to keep it that way so when I bring it to the other side, they're positive sign. You guys can work it at home so you can see it works out. So that's a weak form. That's a weak form right there. Any questions on that? Very quick, very simple. There's a question out there.
Just a general question about your setup. Are you saying that heat into the system is positive or negative?
Excellent. Excellent question. So the trick, by me making this minus and minus, so the question for the video is, how do I choose a sign convention, and how does that imply onto what's positive if it goes into the system or out the system? So it turns out that if you make this minus and minus, and you bring this to the other side, you can see quickly it becomes positive, right?
Okay.
And so it turns out that this Q's, when it's into the system, is positive. You don't have to worry about it. So it's very quick. It's very quick to understand that. So if I have 50 watts coming into the system, you know it's positive, and you don't have to worry about it because it will be in the other side, and it will be very obvious. And I'll give you some examples on that so you can see. So not only by making it this sign convention, changing the sign convention here is very powerful, it makes these two signs minus. I bring it to the other side, they become positive. And not only that, physically it makes sense because I bring, if I put heat flux into the system, I know it's positive, if I subtract is minus. So it's very convenient because of that. Great question. So hey, I'm done. I have the weak form. You guys know the steps. I can actually stop now, but I won't. I have the approximate solution to the problem. I know the basis functions. Remember, some of you were getting concerned. How do I find these basis functions? How do I find these basis functions? This is systematic. You know how to get these basis functions. It's the same way every single time. Ni, Nj, and Nk are these guys for quadratic. For linear, it stops there, right? And you know how they look. I already showed you that in the last lecture. I don't want to repeat it again. And in fact, I think I do anyway. But here is your shape functions. And then n times t. N is the matrix of shape functions. And then t is the unknown nodal quantities for this element that's quadratic right now. But it could be linear. I could have a linear element instead. All right, so that's my element there. 3 nodes, single element. Yeah. And here, Qj and Qi. Going in is positive. Okay? Excellent. Hey, so now I take the weak form. I want to look at the weak form and say, oh, I have to take derivatives. Let me get prepared for that. That's how you want to think about it. I need to get prepared for that, so let's get ready. So T prime, 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 prime. Okay? So let me call this a new matrix B, and I'm doing that so I don't have to memorize this. I just call it B. You know that anytime I say prime, that's basically B. Okay? Times T, I'm sorry. So all I have to do is plug in the approximation here for T. I select T tilde. For V, I select N transpose. We already covered that. So all I've done here is, you can see here, T prime became BT. So that's this guy here. Ka is that. And then bring the V prime ahead. Make it B transpose. That makes sense. If you're wondering where they came from, all we did there is for V, we selected each of these shape functions for the 3 equations. So for the first equation, V is Ni. For the second equation is V Nk. For the third equation is V and J and really is prime for each of them. So that's the transpose, which is basically B transpose. And B transpose now is a 3 by 1 matrix. This is a 1 by 3, so I get a 3 by 3 there. T is nodal quantities. They're unknown, so that's not dependent on dx. Okay? And then when I look in here, for T, it's easy. For T, it's just n times T, which was in the previous page. N times T. For V, I have to make it n transpose. So anytime you make a transpose, just bring it at the beginning. Okay? So you can keep the matrix being 3 by 3. You know you're wrong if you put this one here really quickly. If I make it n times n transpose, it's wrong because then I get a 1 by 1 matrix. So just keep that in your mind as you're working the problem. All right, so that's my matrix. T infinity, I don't have to do anything because that's a film temperature, fluid temperature. For V, again, I have n transpose times AQ. Q is a heat generation, internal heat generation. And then I have these two guys, which are basically Q, basically the matrix of concentrated forces, right? Here it is. So that's the stiffness matrix. Stiffness matrix, because we don't have a stiffness matrix in heat transfer, but the equivalent of that is that the first term represents the conduction, the resistance to conduction. The second one is convection, this term here. And then you have Ti, Ti, Tj. And then this represents, and by the way, I brought the T. Each of these had T's, right? So I brought that out. And so these have basically are forcing functions. These are your forcing functions. These are due to the convection. This is the heat generation. And this is the concentrated forces that you may apply if you want to. Okay? Any questions on that? Any questions? There's a question in the back.
Wait, could you go back a slide?
Yeah, absolutely.
Where does the left B transpose come from?
Where?
Yeah. What does that correspond to in the first E equation?
So V, for V, you're going to select each of the basis functions, right? What are the basis functions? Ni, Nj, and Nk. Well, that's N. You basically have a matrix N. N is transposed because you're doing it for each equation. Okay?
I guess I'm asking in the first term, why is it B transpose and regular B also?
So the question is why I have a B and a B transpose. Is that your question?
Yes.
So the answer is because I have a T prime. When I substitute T prime, that's BT. And then when I substitute V prime is basically this matrix right here, but transposed. And that's B transpose, isn't it? So if I just put B transpose after that, after the B, if I just kept that same order, B times B transpose, that would be incorrect. Because this matrix is 1 by 3, and then the B transpose is 3 by 1. So I get a scalar quantity. That doesn't make sense. It needs to be 3 by 3. Okay? Follow? Excellent. Finally, I derived. That's my element formulation, by the way. I just finished my element formulation. That's where it stops. Then I can take step 8. I can assemble the system together, right? Because I will know how they're connected. And then I'll post-process. That's the error. Step 9 is post-process the results. I'm sorry. Okay, Aaron, you have a question?
Yeah, so K and A are scalar or?
K and A, conductivity, and it's a scalar quantity, conductivity. So you know the conductivity of the material, just like you know the modulus of the material, right? In structural mechanics problem. Okay? And there are experiments that you can do to get the conductivity of the material. And A is a cross-sectional area, which can vary as a function of length, right? Just like we did the bar problem that was varying cross-section. Very good. Okay, P is the perimeter. P is the perimeter of, if you have a constant perimeter, that will be say it's a circle, cylinder. So P here becomes 2 pi r. R is the radius of that rod. And then you integrate that over the length. That makes sense. That the surface, the outside surface is exposed, right? So it's 2 pi r and the length. So that's where that comes from.
And this equation is only for one element?
This equation is true for one element. I derived it for one element.
Even in one element, we cannot different conductivity.
So if you have multiple elements now, right? And let's say I have the first 3/4 of the material is steel. The remaining material is aluminum. Well, then I'll put elements here, and I'll stop right there where the aluminum and steel boundary is, and I'll put a new element that represents the aluminum. Right? And for aluminum, I will use the appropriate conductivity. For steel, I will use, thank you for giving me a good homework problem. He just gave me a great homework problem. Okay, thank you. Post-process, step 9. So that's an error. It's post-process. Okay. Let's look at some examples. Well, I didn't do an example here. I did a linear element first to show you what you get. For linear elements, you just get Ka over L. Remember, in structural mechanics, you get Ea over L for a bar. But for heat transfer, you get Ka over L, but 1 minus 1 minus 1, 1. The assembly process is the same process. If the heat enters the system, it's positive, to answer your question. Q has a unit of watts, which is heat. What else we got? We're good to go, I think, with some examples. Example 3, A. This is the first example. So the example is calculate the nodal temperatures. Find the temperatures here. Okay. Here I'm specifying it to be 200 C. So only place I don't know the temperature is here, 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 and here. I want to bring in no heat applied to this node. I want to take 200 watts out from that, apply no heat here, and input 500 watts here on purpose. I give you the length, 1 meters for the whole thing. The cross-sectional area is A is 1 meter squared. All of that is done on purpose. K is 10, so I can just quickly do the calculation. Ka over L. I can do the calculation really quick. That's the purpose of that. What else we got? Yeah. That's it. For each element, quickly. You can they're the same size, right? So it's the same for element 1, 2, 3, 4. Okay. Then assembly, same process, just assemble it using the same process we discussed before. Connectivity code, use that to assemble it. I know the temperature here is 200. These are unknowns. Okay. Q1, since I'm specifying the temperature, there must be a heat that's been applied that keeps that node at that 200, right? Or removed. We don't know which way. But we know there's something being applied to keep it at 200. You agree? So we don't know what that is. But for the other ones, we know because I told you about it, and that's what you get for temperature. At the other, if you want to calculate it, invert this whole thing, you get these numbers. Okay. It actually matches the exact solution too. Really good. I didn't plot it here, but it does match. Wall temperature. Let's look at a different example. In this example, I have a wall at 200 C. Okay. Okay. There's a heat source inside the wall. There's a 400 watts per meter cubed. There's no heat flow here at this boundary, so there's nothing happening here. It's adiabatic, basically. So that's what you see here is Q at 1 meters, because this is 1 meters long. That's 0. The conductivity is K equals 25. Use 4-element solution. Okay, and I'm not losing any heat along the length. Any questions? You want to memorize that picture? You won't see it again. Very quick. It's easy. Keep this at 200 C. There's a heat generation inside, and I'm not losing any heat from the boundaries. Okay. Very quick problem. 4 elements, and I think these are linear elements. I'm not doing quadratic in this example. Again, you can calculate this very quickly. Okay. For heat generation, this became 50 and 50. Okay, and you can check that makes sense. I won't do it now, but you can check it at home. Well, actually, you can check it here. When you assemble the whole thing, You get 50, 100, 100, and 150. Okay. Add this together. What is that? 400. Well, I just told you that I applied 400 internal heat generation. But when I did the integral of Q against the shape functions Ni and Nj is only a linear element, it told me how to distribute that load. You can actually do it by memory too. I have 400 heat generation. Well, then put 100 here, 100 here, 100 here, and 100 here. You agree? So if I have 100, put 50 in each node, 50 in each node. Well, isn't that what I got here? 50 and 50. I didn't do the integral. I did the integral, but you could do it by using memory. Assemble it. Okay. I'm not losing any other heat. Nothing else is specified. T1 is 200. You're specifying that, so you can get the rest of the temperatures. And that's what you get. Okay. I did it here. This actually makes a lot of sense. It's telling you I'm not losing a lot of heat. Maybe 400 watts is not enough to really heat up this bar too much. That's what's telling me physically. Okay. Second example is okay. This is an interesting problem. You have to, and Abaqus can do this as well. Okay, it's an end convection problem. I'm only applying convection at this node. Okay, and at this node. So these two ends are subject to some fluids there. And this node is subject to this fluid. Okay, it's a very quick thing to do. Just don't worry about it. Just think of this as a heat flux. You follow me? Isn't that a heat flux? If I have this node is hot and this is cool, what's happening? I have a heat flux. Is it going in or out? If this is hot and that's cool, which way I'm going? Out. I'm losing heat. Okay. If this is cool and that's hot, which way I'm going? In. Right? Same format, element formulation. Okay. And the only difference at this node and this node, and that node, I actually have a Q. In this case, that Q is just the film coefficient, the fluid coefficient times A, and the difference between the fluid, okay, minus the temperature at that node, okay. And for this third node, same process. I have convection again at that node, and it's going to be H3A T3 infinity minus T3. Now, I chose this way because this way guarantees that I get either heat in or heat out correctly. Okay? So the way to know that is that if I go from the fluid into the node, so I have from the fluid into the node, that's a positive heat flux. Now, if this is cool or this is hot, doesn't matter. It's going to give me the right sign. I don't have to worry about it. You can check it at home. It's going to be correct. Just do an example at home. Make this 50, make this 100. Then switch around, make this 100, and then make this 50. And then plot the arrow, and you will see that it's going to be correct. Okay, this is great, but there's a problem. There's a problem, and the problem is that when I assemble it, and I have this great equation, T1 shows up here and shows up there. And T3 shows up here and shows up there. So this is what is called a mixed boundary condition. It has essential boundary condition and also has a natural boundary condition. Okay, it's a mixture of the two. I have an essential type of boundary condition showing up on the right-hand side, but I also know that this is like a heat flux. So I have a mixed type of boundary condition. Okay. And Abaqus can actually solve this, and what it will do, it will actually try to solve this by actually arranging the matrix. So I can now, can you see that each of these equations are their own? I mean, these are separate equations. Don't you agree? Can I bring this T1 times H1A to the other side? Bring this T3 times H3A to the other side? And then I'll just have T1, T2, T3 again. Nothing to worry about. So we augment the matrix, we rearrange it, and I get the H1A there, H3A there. And now These are known quantities. I know the film coefficient, the fluid coefficient, the heat transfer coefficient. I know the area. I know the fluid temperature. I know all this stuff. So then I can get the temperatures. Notice how in this problem, I'm not specifying any temperatures. But yet, when you invert this matrix, it won't be singular. It's going to invert very good. Why? Because anytime you solve a physics problem, if it's well-defined and makes sense, you're going to get a solution. Okay? But if you have a physics problem where maybe I had a bar, a single bar, with nothing, no temperatures applied, I apply heat fluxes. Well, I have a problem here. I can get infinite solutions to the problem. So math knows when physics is incomplete, and vice versa. Math knows when physics is complete, because it will be able to invert it. Okay? Keep that in your mind as you work these problems. If I have a convection, but now the convection is along the rod. Remember that I showed you that I can have it along the rod too? Yes?
Yes.
If you remember, I had this term pH, T, T infinity, all this, right? If I plug in the shape functions for linear elements, I get this matrix here, a new matrix that you had not seen before. I was getting Ka over L, that one. Now I'm getting this new one when I have convection along the rod. Okay? And then these guys go to the other side, just like before, and this one goes to the other side. The Q is this one, and this Q has been integrated over the 0 to L n transpose AQG. I'm calling it QI and QJ, just like before. The thermal dot vector, if I were to calculate it for linear elements, QI and QJ, you basically get AQGL plus HPLT infinity. It comes from this one. So n transpose pH T infinity, that goes to the other side of the equation. That's this contribution. You basically get this. Okay. So work it out at home. You'll see. You get what I have. Okay. Yes.
Yes.
It's the first time I'm kind of skipping a step, so I hope you're not losing it. But trust me, it works out. Use Mathematica. It's going to work out very nicely. Okay, example. I have a cooling fin. This is using heat transfer problems. In a heat transfer problem, I have a 330C at this node. This whole end is exposed to convection. Even this end is exposed to convection. So this whole end is exposed to fluid. There's a 30C. Maybe it's air, but it's exposed to something, right? And I give you the conductivity. I give you the film coefficient. I give you the H. So I give you the heat transfer coefficient for this fluid that's surrounding this. And there's experiments that people do to determine this, so you don't have to worry about it. So if you're working on, say, a nozzle of an engine, right? And I want to know the combustion gases. What is the H for that combustion gas? Well, in that case, you need fluid dynamics, computational fluid dynamics. It gives you the velocity of the fluid. It tells you the properties of the fluid. And with that information, they're able to tell you what the heat transfer coefficient is. Okay? Or if you have a capsule, a space capsule re-entering Earth. Well, I know the computational fluid dynamics from there. I know the velocities. I know the pressures acting on the surfaces. And I can do experiments to calculate what these heat transfer coefficients are, too. You can either determine that experimentally or make some estimations, right? But H is a property of that fluid, okay? And H is going to be different. It could go high numbers if you're looking at high velocities fluids. If I had, you agree that if I have a, let's take the Samsung 7. I have a Samsung 7 that's burning, and I take a water hose and I shoot at it 100 miles an hour. Will that cool faster than just me putting on just water? Because I'm shooting at a high velocity, well, then the H is going to be higher. You're going to lose, right, heat faster. So this is a heat transfer coefficient, and it depends on the velocity of the fluid too. Okay? In this case, I'm just giving you a lecture on something else. But in this case, it's just cooling fin, so it's kind of sitting in there, or some gas. So we're going to use a 3-element approximation in this example. Okay, I think I gave you all the properties that you need to do. If you want to, reproduce this at home, you can. So you can calculate the stiffness matrix. So not the stiffness, the conductivity matrix EA over L. This was your pH. That pH term. That was this one divided by 6. And then the element matrices for element 1, element 2, 3. And then here, what you see is the 38.4 is coming from this term here. It's coming from this term. N transpose pH T infinity. When that goes to the other side, that's where there's 38.4 is coming from. Okay. And on the left-hand side, what you saw here is I'll just plug in these numbers. That's all I did, just plug in these numbers. Okay. Yeah, so just get every element, values, get the thermal load vector. If you calculate this, I think you'll get 38.4. So if you calculate this. Assemble it, but I have a problem. Because in no T4, not only have the 38.4, but I also have that end is exposed to convection. So again, I have to put HA T infinity minus T4. T4 shows up in both ends. And also T1 is 330. So you have to basically bring this to the other side somehow, right? Arrange it. And then solve for T2, T3, and T4. Okay. I'm not showing you all the steps because I think at this point it's basic. Okay, so let's take the final example with quadratic elements. So I did this example, and so I have case number 1. I have a single element, but it's quadratic. I was just showing you heat transfer with linear elements because I had not done that in the previous lecture. So I covered that. Now I'm looking at quadratic elements. So a single element, and then I'm specifying, in this case, I'm specifying temperature here and here, but not here. Just a single element. So same process. Plug it in. This is 100, 100. One equation, solve for T2. Okay, so that's a simple one. Case 2 is I have an N heat flux. So here I have 200 coming in. Keep that at 100. Middle node and this temperature are not known. So I don't know this temperature or that temperature. Same process. This is 100. But now I have a heat flux coming in at 200 in that end. Now again, solve for two equations, T2 for T2 and T3. And once you have that, you know what heat is necessary to keep that at 100 degrees. Okay, so you can put a reaction force here. Can you make a note so I can put some Q here so they know that that's basically a reaction force?
Yeah, actually, I was going to ask you about that.
Yeah.
Yeah. When we are solving a 1D problem in
Yeah.
elasticity, and we are interested in the internal reaction forces.
Right.
After we solve the global problem, we get back to each element and we can find each reaction force
Right.
per element. In the case of the heat transfer problem, what those heat flux reaction means?
It's basically the heat that's required. You need heat to keep something at the temperature that you want.
But that heat is applying at the boundary, right?
Yep. You need to apply some heat to keep it at that temperature. So the question for the video is, what is the physical meaning of the analogy to a reaction force in elasticity? In a mechanics problem, okay, in mechanics problem, if I'm keeping something at a particular displacement, there's a reaction force that it takes to keep that displacement at that value. Is that correct?
Yeah.
In a heat transfer problem, to keep a temperature at the same value, you need to apply either heat or remove heat to keep it at that temperature. Otherwise, that temperature is going to either go up in value or down. But if you want to keep it at that temperature, you need to either add heat or remove it. Okay? You need to do something about it. So I'm missing something here to say that I can calculate what that heat is to keep it at 100. Okay. Third example is in convection. Another example there. Okay, I'm calling the temperature of the fluid here T infinity, or TA I called it. And the heat transfer coefficient, I made an M for this here. So the H is equal to M. Same process. T1 is at 100 here. T2 and T3 are unknown, but now I have MA times TA minus T3. That's my heat flux, basically. Now T3 shows up on the right, and T3 shows up here, so I have to bring T3 to the other side. And you can see here how to do that. So I have my conductivity, my convection, and then I have the term that I have to bring to the other side. These are 3 by 3, right? You agree?
Yep.
3 by 3, so 3 by 3 plus 3 by 3 gives me a 3 by 3. And I know T1 is 100, T2, T3. In this example, I have no conduction along the length, though. So I don't have a conduction along the length, just on the end. So this is 0, really. And that's 0 also. And I have no internal heat generation in this example. Q is 0. The only thing I have is this term, in that example I gave you. Okay? Now you can solve for the middle temperature and the end temperature very quickly. And finally, I have some observations to make. We have developed an approach to solve ordinary differential equations using finite elements. We're finally using finite elements. And I've shown you how to do this with an elastic bar and a heat transfer problem. But the approach, I don't know if you realize this, it's not quite systematic yet. It's not quite consistent yet. Okay? Why? If we look at one of our examples, where remember I had those elements of different sizes? Yeah? I had to recalculate the shape functions for each of them. Okay? If you go back to this example where I was using Mathematica, I have to recalculate the shape functions for each element. Secondly, I had to take derivatives of those shape functions. And those derivatives, if you remember, let me take you back there because I think some of you are forgetting. I'm going to show you very quick. We'll get there very, very quick to that example. Okay? And the example was a bar problem. And if you see here, the shape function for element 1 for the problem that had to do with this. This is the problem. 2 elements, different sizes. If you saw this problem, the shape function was different for each element. You can see that here. And not only that, the derivative is different. But I have to calculate it each time. And not only that, the integral also is different for one element to another. This one went from 0 to L. And the next one went from L to, well, the shape functions are different. Derivatives are different. And the shape functions go from L to 4L. So as you see here, right, as you see here, these calculations have to be repeated. Okay? And so what we're going to do next is to figure out a clever way of not having to recalculate these shape functions, because these are numerical calculations that cost computational time. So if I have a way of keeping the shape functions the same for every single element, I don't care what size I have. I could have an element this size or an element this size, but the shape functions are the same. If I can make my integrals go from, say, 0 to 1 for every single one of them, that'll be awesome. Because then everything is consistent. And that approach is getting me now closer to a more systematic approach, an approach that can code up or, quickly execute with no issues. Okay? And that's convenient because if I look here at an airplane, and I have element sizes that look like square. Some of them look like trapezoid. Some of them may look quite skewed, right? If I can map all of those to look like a square, right? And they all look the same, and I know how to solve the equations for a square, that's all I need to know now. If all I need to know is how to solve the part, if I told you that to solve an airplane problem, I need to solve the partial differential equation for a square, and I'm done. Would you be happy? I think so. But if I told you I need to solve it for at the discretized domain, and it's going to have, every single element is going to look different from each other, and I told you now go ahead and solve it, I think you'll be a little bit concerned. But if I can solve it for a square, and that's all I have to do, I think you'll be very happy with what we're going to do next. So that's where we're moving on towards, okay? And once we cover that, we're basically at the very depth of finite elements. We'll be, we'll have finished 1D, and then we can move to 2D and 3D, okay? So with that, thank you very much for attending. And you have a good weekend.